Okay, yesterday we discussed about ripple carry adder, right? So there we mentioned something about like instead of using assign statement, we use something called as full adder FA01, right? FA0, FA01, like that, right? So did anyone got the idea why we are using that inside Verilog code? I'm talking about this. It's my screen visible, right? So did anyone of you got the idea why we are using full adder FA0, full adder FA1, like that? Okay, look here, I'm going to explain. Okay, here, oh yeah, yeah, to do multi-bit addition. But why did we use instead of this like full ladder, some instead of assign or always block in the design code? Why? Yeah, for 4-bit we need full 4 adders. Yeah, here we like a ripple carry adder. We are going to add 4-bit input data, right? So you are going to use full adder 4 times. Okay, 4 full adder. It will give you like something FA0 will give 1 bit, fa1 will give 1 bit, fa2 will give 1 bit, and fa3 will give 1 bit. Okay, if you sum up that 3 bits, then you are going to get 4 bit as a sum. Okay, so what I'm trying to say is in previous Verilog codes we use something called as assign statement, right? Assign or always block. So why is that missing in this code? No idea. See here, I'm going to explain. Listen carefully. Okay, in Verilog, we have 3 types of modeling. Okay, first one is design is using by writing continuous statement. No, no. See, listen here. I'm going to explain. Inside Verilog, we have 3 types of modeling. Okay, so what are the 3 types? The 3 types are data flow modeling, behavior modeling, and structural modeling. Okay, so just write these 3 types of modeling. Okay, so the three, yeah, behavioral, structural, and data flow. Yeah, behavioral and like if you think about what will be the difference between this type of modeling means, the one we are using is called as structural modeling. Okay, so what we have written inside this design flow is, right, you can see the design code, right, of ripple carry adder. Before writing this design ripple carry adder design, we are need to implement full adder design. Okay, so after implementing that full adder design, you need to write down this ripple carry adder uh, beside like after that. Okay, after writing full adder design, you need to continue with ripple carry adder. Okay, so if you do like that means, so when you have in 4-bit multi ripple carry adder, you are going to use 4 full adder, right? So it will take like this. Look here, what it is like, it thinks like a full ladder. Oh, it's calling full ladder, and it's something like like connecting design and test bench. Here you can see that, right? So it was something like that only. Okay, it's look like something like that. And this is all like port mapping. You are mapping that full adder port to ripple carry adder port. Okay, so this is what structural modeling looks like. So okay, so this was the one, like I gave you a task right yesterday to find out why I've used like this. So if you are going to see this in EDA playground, means it was some looks like somewhat like this. Wait, I will show that also. Look here. This is what EDA playground looks right. See here, this is my design code, right? What I have done in the design code, first I have implemented the full adder module. After that, I have designed ripple carry adder, right? So if you do like that, means this full adder is coming from here, okay? So it's going to map this full adder with this ripple carry adder design, okay? It's going to tell I'm going to create a full adder with the name FA0, and it will map, and it's going to create another full adder FA1. It's going to map the values like that. It's going to happen, okay? So this is what structural modeling looks like. After that, as usual, you are going to create a test bench and apply the some of like test cases and check whether your model is running, and you will get something what like this, right? So this is what your ripple carry adder output looks like, okay, using structural modeling, okay? So just keep that in mind, okay? So next, today we are going to learn a new concept, okay? What is that concept is called as? It's called as carry look ahead adder, okay? So as usual, so as we know, a ripple carry adders work correctly, right? So in when it comes to VLSI design, correctness alone is not enough, right? So like I think if something is you have designed is working correctly, but in VLSI, correctness doesn't only matter, right? It needs like efficient, and it should be fast, right? So on that basis, you are going to you are going to implement this carry look adder, okay? So why we are using this carry look ahead adder? Because it helps to increase the speed, okay? So the limitation of ripple carry adder is speed, which is like can be maintained using carry look ahead adder. Why? Because look here, inside ripple carry adder, like for how was full adder bits for calculating? It was calculating in series, right? So when come to like carry look ahead adder, it calculates parallelly, okay? So that's why it increases speed. How it increases speed means, look, if we have four full adder, okay, four are working accordingly like simultaneously. If first one full adder is working, then all three will be working at the same time. So when it comes to ripple carry adder, it was connected seriously, right? It needs to send its carry into second full adder, and that carry into third full adder, like how it's going to work, right? So that's how it's going to increase the speed inside the carry look ahead adder, okay? I hope everyone got my point. So as I said, in RCA is nothing but ripple carry adder, where every full adder waits for previous carry. That means FA2 waits for FA1, FA3 waits for FA2, FA4 waits for FA3, right? Like this, there it create a propagation delay. Propagation delay is nothing but like propagating that C in value as C out, right? So there will be delay something like it's need to first FN1 needs to be calculated and it's sent C in as C out to second full adder. Like this is going to work. But this is what you're going to achieve inside a carry look aheader. So you are removing that propagation delay inside carry look aheader. Okay. So for a for giving you a real life exam explanation means imagine as four students are passing a notebook one by one. Okay. So second waits for third first one and third waits for second one and fourth waits for third one. Okay. So there you will get a lot of time, right? So if four of them passes like each at a time means there will be no propagation delay. So that's what I'm going to explain. Okay. So why this carry look adder is needed? Why we need that? Like in processor like Intel or AMD, like millions of additions happen every second, right? So like if you have some processor, there will be like only one task will be not achieved in a second, right? Like nanoseconds or something. So there will be many tasks going on in a particular second or millisecond. Okay, so that time carry look ahead adder will helps you to dismiss that propagation delay. So what is the core idea of carry look ahead adder? So the core idea of carry look ahead adder is that it predict carry early. So like it can predict what's the first going to decide, like what it's going to send a carry in as like, and it decide basis on that, and it will predict the carry early. Okay, so just keep that in mind. So this is what triple carry adder looks like. So inside carry look aheader, we add something important terms. Okay, one is called generate signal, and another one is called propagate signal. So what is generate signal? What does the generate signal defines? Generate signal is going to define if both inputs are one, carry is generated. Okay, like what I said, how your carry will be achieved. Take example as full ladder. If A and B are one, both are one, you are going to sum as you are going to get sum as zero, right? And carry as one, right? Like that only this generate signal checks for both inputs. Okay, if both inputs are one, then it will think I need to generate a carry. Okay, so this is how it's going to work. So what will that Boolean equation of that generate signal will becomes? Obviously like what does this definition says? It's going to generate carry signal when both inputs are one, right? So there is a gate which will act in this situation, right? Think of AND gate. When will AND gate achieved? AND gate can be achieved when both inputs are one, right? So in this time, this generate signal is the same as AND gate, right? So you can write like this: AI AND gate BI. Okay, this is how you are going to create a generate. So where it comes to propagate, so what is the term propagates do there? So it's going to tell that if one input is one, incoming carry can move forward. Okay, so it's telling that if any one of the input, either A or B, becomes one means incoming carry can become one. Okay, so carry in will become one. Okay, at that time. So what this gate is like, what gate can be achieved here? XOR, right? What does XOR do? Only like output will be only activated if any one of the outputs should be 1, right? Not both should be 0 and both should be 1, right? If any one of the means 1 means it's going to create output, right? So propagate will looks like that, okay? So and if you calculate these generate and propagate signal, you are going to get some, okay? Inside some you need to do XOR condition for both propagate signal and carry in signal, okay? That when you do that, you're going to get the sum, okay? The final sum. Look here, what we have here, a is 0 and b is 0, right? So what will ga will become 0, right? And p propagate signal also will become 0, right? So that carry action is called as kill carry. Kill carry means like we don't going to achieve anything if the both input are 0, right? So it's like you can state that as kill carry, okay? So if any one of the input is going to 1 means propagate signal is going to be achieved, right? So at that time it has been 1, okay? So the carry action is called as propagate carry. Same for the next case also, propagate carry. And this will be generate carry means generate, like if both the inputs are 1, then you are going to generate the generate signal, right? So that's why it's called as generate carry. Okay, look here, in coming to CLA we have something called as carry equation and parallel generation, okay? In carry equation and parallel generation is nothing but how the things going to be achieved inside that carry expansion, okay? So look here, C1 equation is nothing but like uh, in what was happening inside that full adder, a ripple carry adder. We are going to connect. We are going to connect that everything into something called as like C1 was connecting to a C out C in for second adder, right? In ripple carry adder, and that C out of second add full adder was connected to C in as third adder, right? So here it's going to predict, okay? So like every C in are going to compute it parallelly using generate and propagate signal, okay? So how that calculation does, okay? In C1, okay, in full adder 1 we will get something like this, okay? Equation will become something like this, okay? P0 is nothing but you have A0, right? When does that C0 works, C1 works when you have like A0 and B0, right? When you have input of like A0 of like think as least significant bit, it's going to work when you have least significant bit, okay? So basis on that your GO and PO will be calculated, okay? That in turn it will be calculated using CEO, okay? So just remember this equation. I will teach how you are going to achieve this equation, okay? There is okay, there is something called as carry main equation, okay? What does that carry main equation look like? C I plus 1 is equal to Gi plus pi ci. Okay, this is what the main carry equation looks like. Okay, so how we are going to calculate the this what you are looking like c I plus 1, right? This is nothing but a carry coming from a first full ladder. Okay, if you apply 0 here, I0, then it will become c1, right? So c1 is nothing but the carry is coming from first full ladder, and c2 is nothing but carry from coming from a second and third and fourth. Okay, this is how it goes. Okay, so look here, what you have gi, what is the formula of gi? Ai into bi, right? So so your carry, like this equation is used to calculate your carry, right? So your carry can be calculated either using gi or using propagate signal. Okay, so like what I said, if you have something both input as one, then your gi is going to determine what your carry will be, right? Or else if you have 1 0 and 1 1, one input as 0 and one input as 1, your propagate signal will going to carry the, like calculate that carry, right? So basis on that your carry equation will look like this. Okay, so this equation tells what will be the possibility of like next carry, like what will be the next carry looks like. Okay, so if you are going to like do create a equation for first carry in. Okay, what will the first carry in looks like coming from a first full ladder? Okay, apply 0 here, I will be become 0, right? gi 0, pi 0, ci 0, everything will become 0, and it look like this: c1 is equal to g0 plus p0 and operation c0. This is what that first operation looks like. So just also apply like 1 now, c2. Okay, c2 g1 plus pi becomes p1 ci, right? P, P1 C1, it will becomes, what will it becomes? C2 G1 P1 C1, it will becomes like this, right? But see, look here, you have C1, right? You got C1 here, so just apply this equation C1. Okay, what you have got C1, right? Inside this C1. Okay, so it will becomes like this. If you need to calculate C3, like C3 is nothing but carry coming from a third full ladder. Okay, apply 3 here, 2 here. Okay, C3, it will become C3 G2 P2 C2. Okay, now you know C2, what the C2 equation looks like. Okay, so replace that C2 equation inside this here. Okay, so it will becomes like this. This is how you are going to achieve, like calculate a carry in based on this equation. Okay, so and after that, this is what your block diagram looks like. Okay, so this is nothing but your generate and propagate signals. Okay, that is being generated. Okay, in generate, like this is what inside your adder looks like. Okay, here in generate and propagate signal, your g0 will be calculated, like g1 will be calculated, g2 will be calculated, g3 will be calculated. Okay, and that cout will be transferred to this carry look ahead logic unit. What does they do? Like they calculate c1 c2 c3 parallelly. Okay, and that will be sent to the sum bit. Okay, sum bit 0, sum bit 1, sum bit 2, and sum bit 3. Okay, Like this you can get 4 bit of sum. Okay, so this is how you are going to calculate the your CLA. Okay, and next is nothing but writing a design code. Okay, so if you are going to write a design code, it looks like this. Okay, see here we are not using full adders. Okay, so we are creating like what's going to happen inside, like parallelly, right? So we have found something parallel equations, like how to calculate c1 c2 c3 c4, like that parallel equations, right? So we are applying that parallel equation here only. And before applying that, we need to know how to calculate g and p, right? And we are also applying that equation also. And this is nothing but everyone knows, like how to create a module and how to name them, like that. So I'm giving like you guys some task. Okay, so why have we written this g and p and c outside the this port? Okay, why have we written? Okay, just find out like why we have written this inside. Okay, when you are in EDA playground, just check the difference. What happens if you put this inside this module and outside the module? Okay, so and after that test bench, you are going to create a test bench and check for the waveform. Okay, so this is enough for this class. Okay, like we have so many concepts, like after carry look adder we need to learn something like carry select adder and the carry skip adder. Okay, so if you learn carry look adder and carry select adder three in the same class, means it will be make you got confused. Okay, so first learn this carry look add adder. Okay, so try to check the difference what I told inside the PDA playground. So if you are guys like they get any doubt, means I will answer in the next class. Okay,